Is it possible to build an anti-gravity machine which shields itself from the effects of gravity? We're not referring to a vehicle like a helicopter. A helicopter still feels the effects of gravity, but overcomes it by creating an upward force. The upward force is the result of an equal and opposite downward force on the air molecules. Similarly, birds and airplanes also feel the effects of gravity, but overcome it by creating an upward lift. For both birds and airplanes, the upward lift on the wings is associated with the downward deflection of the air. Any existing or future vehicle, which creates an upward force to overcome gravity, is not really an anti-gravity machine, since the effects of gravity are still being felt. In much the same way, balloons and airships are also not anti-gravity machines. They float because they are less dense than the surrounding air. Air is a type of fluid. Inside a fluid of a given density, gravity causes denser objects to sink to the bottom and causes less dense objects to float to the top. This is not anti-gravity, but just an example of how gravity works. To understand the nature of gravity, suppose we're in deep space with no gravity present. Presume this box accelerates upward as shown. To Victoria, it appears as if gravity is present, causing her to fall downward. Albert Einstein's general theory of relativity states that it's impossible to distinguish uniform acceleration from a uniform gravitational field. Hypothetically, suppose we built a true anti-gravity machine, which shields itself from all the effects of gravity. If there is a gravitational field present, the anti-gravity machine would not accelerate. Though, suppose that there is no gravitational field present, but instead the box containing the machine accelerates upward. The anti-gravity machine would be forced against the floor of the box as shown. This means that it would be possible for someone inside the box to differentiate uniform acceleration from a uniform gravitational field. Therefore, the existence of an anti-gravity machine would violate Albert Einstein's general theory of relativity. Here's another way to look at it. If a box is falling in a uniform gravitational field, Albert Einstein's general theory of relativity says that Victoria should feel weightless, and she should not be able to tell that gravity is present. Nevertheless, if we add an anti-gravity machine inside the box, then as the box starts to fall, the anti-gravity machine will initially stay where it is, until it is pushed against the roof of the box. This would allow us to know that there is gravity present outside, which again would violate Albert Einstein's general theory of relativity. Some people might point out that it's always possible to tell that there is gravity present outside, because the gravitational field created by the Earth is not uniform. Yet, suppose there is a uniform gravitational field present throughout the entire universe, pointed upward as shown. This upward uniform gravitational field would exactly cancel out the downward gravitational field from the Earth at the one point that we're interested in. From this perspective, a particle at this one point is not undergoing any acceleration at this moment in time. Instead, the upward uniform gravitational field present throughout the entire universe is causing the Earth to accelerate upward towards the point. There is no experiment we can perform to prove that this is not the case. It is in this sense that general relativity says that it's impossible to tell if there is a gravitational field present at any particular point. One of the consequences of this is that, in the absence of air resistance, in a given gravitational field, all objects must fall with the same acceleration, regardless of their mass. In Newtonian physics, this was explained by saying that objects with greater mass feel a greater gravitational force. Victoria feels weightless in a box falling directly downward, for the same reason she feels weightless in a box orbiting the Earth. This is because Victoria and the box stay together, giving the appearance of weightlessness. General relativity says that Victoria and the box stay together because they both follow the same straight line through curved space-time. In general relativity, gravity is not a force. A straight line on a curved surface is called a geodesic. General relativity says that in the absence of a force, all objects follow a geodesic. This is another way of understanding why an anti-gravity machine is not possible according to general relativity. An anti-gravity machine would not be following a geodesic, despite the fact that there are no forces present. In fact, an anti-gravity machine could escape from beyond the event horizon of a black hole, which is a clear violation of the known laws of physics. The event horizon of a black hole is the point beyond which not even light can escape. Here, the arrows represent rays of light. Space can expand faster than the speed of light, but nothing can travel through space faster than the speed of light. Therefore, since light can't escape from beyond the event horizon of a black hole, neither can anything else. The rate at which time flows is affected by gravity. This is necessary so that it remains impossible to differentiate a uniform acceleration from a uniform gravitational field. If we send light pulses from the top to the bottom of the box as the box accelerates upward, the frequency of the light pulses will be greater at the bottom. From the perspective where the box is standing still and there is a gravitational field present, the gravitational field causes time to flow slower at the bottom, causing the clocks at the bottom to measure a greater frequency for the light pulses. In both cases, the frequency of light pulses is greater at the bottom of the box than at the top. And we can't tell the difference between uniform acceleration and a uniform gravitational field. In a uniform gravitational field, different clocks will move at different rates, depending on their distance from each other, along the direction of the gravitational field. In a uniform gravitational field, different clocks will move at different rates, depending on their distance from each other, along the direction of the gravitational field. This is critical to understanding why moving in a straight line, which we call a geodesic, creates the appearance of a gravitational force. On a curved surface, a geodesic can be thought of as the path taken by an attached car, with its wheels always pointed forward, with the left and right wheels always rotating at the same rate. In general relativity, we're not just moving through a curved three-dimensional space, but through a curved four-dimensional space-time. From the perspective of the car, it's always moving forward only in the time dimension. From the perspective of the car, it's always moving forward only in the time dimension. Objects are always moving forward in time. Time near the Earth is flowing more slowly than time further away from the Earth. This needs to be taken into account when applying our analogy of the car with its wheels always pointed forward, with the left and right wheels always rotating at the same rate. Once this is taken into account, we can see why objects appear to be gravitationally attracted to the Earth. Images and descriptions like these are only analogies and are never the complete full story. To understand the full story, it's necessary to understand Einstein's field equations. This is covered in the video titled Einstein's Field Equations of General Relativity Explained. Special thanks to all the people supporting this channel on Patreon. Your support is very much appreciated.